Now we're going to do the same problem that we did before, namely this one, where we had to do integration by parts twice. Only we're going to do it by what I call the short method. The short method just gives you a way to write down these substitutions without having to formally say u equals this and dv is equal to that. All right, so here's the way it works. There's our problem. The integral of x squared plus 3x times e to the 2x dx. In one column, we're going to have the u's that happen, and on the other, it's going to be the dv's. So to begin with, you look at this problem. U is what? X squared plus 3x, and dv is e to the 2x. Now, it's e to the 2x dx, but we're just not going to write dx because it's the short method. All right, now what do you do with the u's? If you go up here and analyze it, every time you have a u, to begin with, u is x squared plus 3x. Next, it's u is 2x, and I'm going to, which is the derivative of the top one. And finally, it's going to be 2dx, which is the derivative of that. So once you choose u, what do? Just take derivatives. X squared plus 3x is our first u. The second u is going to be 2x plus 3, the derivative. And the next one is just going to be 2, its derivative. Life's a lot simpler. Now, what did we do with dv? The answer is, to figure out what v is, we had to integrate. So in the u column, we differentiate. In the dv column, we integrate. Right? So the first one is dv. The next one is our first v. Right? We integrate. So you take e to the 2x, and when you integrate it, you get 1/2 e to the 2x. And if you integrate it again, you get 1/4 e to the 2x. Now, what does our integration by parts formula say? It says it's uv minus the integral of v to u, right? There's always a minus that kicks in. What that means for the short method is, first, it's just u times, here's our first v. But next, it's going to be minus the next uv. And then, if I had another one, it would be minus that, which is a minus, or a plus. So the bottom line is, these signs alternate. Plus, minus, plus. Now, where do you stop? Well, the answer is, you stop when you can integrate the term that goes straight across. See, these go diagonal, diagonal. Eventually, you're going to say this integral, because that integral is going to be v times du. V times du. All right? So you keep taking derivatives and you keep doing integrals until this integral, which is what it turns out to be, is something you can do. All right, so what's the word? The word is start with u, take derivatives. dv's got to be everything else, integrate. The terms alternate in sign. It goes plus, minus, plus in this case. And you go diagonal, diagonal until you can finally integrate what's straight across. All right, so let's write down the answer. It's u, x squared plus 3x, times dv, e to the 2x divided by 2. There's that piece. Then I have a minus the next uv, which is what? 2x plus 3 times 1/4 e to the 2x. That's what this is. Now I notice this integral I can do. And what is that integral? Well, it's plus what? Twice 1/4 e to the 2x dx. Now once I go across, that's my last term, and it is an integral. Get it? All right, so if I integrate that, I claim I'm going to get 1/4 e to the 2x. I have to be careful. This 1/4 comes out to give me a half, but then I integrate e to the 2x dx, which I claim is another 1/2 e to the 2x. All right, well, once I've written down this integral and it goes away, I write a plus c, and lo and behold, there is my answer. All right, now let's go back and compare this answer with this one, and you should get a warm fuzzy feeling that it is in fact the same answer. All right, that is the short method. You pick your u, you pick your dv, you integrate your u's, and you differentiate your u's and you integrate your dv's. Got it? All right. Now the examples we've seen up to this point have been a polynomial times a transcendental. A polynomial times a transcendental. And in that case, u is always the polynomial. Now, I want to look at another integration by parts where I have two transcendentals. You see I have a sine x and an e to the 2x. Now, with respect to that, it really doesn't matter what you let u be or what you let, well, and then once you decide on u, dv has to be everything else, right? By the way, unlike up here where u becomes a polynomial of lower and lower degree, this u isn't going to do that. And so the question is, well, how does this work then? All right, so here I've got the integral. I let u be sine x, dv's got to be everything else, e to the 2x dx. Then du is what? Cosine x dx, and v is the integral of e to the 2x, which we saw previously was just 1/2 e to the 2x. Now if I plug it into my integration by parts formula, I get what? uv sine x 1/2 e to the 2x minus the integral of v 1/2 e to the 2x du, which is cosine x. All right, now I'm there. Well, I can't integrate this any better than I could integrate this. So now I claim do it one more time. Although now there's a Southern Missouri phrase that says don't change horses in midstream. If I let u be sine x, that is the trig function, I need to let u be the trig function again. If you don't do that, then you're not going to get too far. You're going to end up with something that's true, but it's not going to be very helpful. All right, so let u be cosine x. Du is minus sine x dx. Dv has got to be everything else, which is 1/2 e to the 2x dx. V is the integral of that, which is going to be 1/4 e to the 2x. So now in this piece right here, I write uv cosine x 1/4 e to the 2x minus the integral of v 1/4 e to the 2x du minus sine x dx, right? So this whole thing is this piece. And then I've got this minus floating around, right? All right, so I clean things up, distribute my minus. This is going to be minus, 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 so it's going to be negative. So I get minus a quarter e to the 2x sine x dx, if I'm careful. How am I any better off? Well, I'm better off because this integral is exactly what I had on the other side. See that? I'm back to where I started almost. How does that help me? Well, if I take this over to the other side, then I can combine those. So that's what I do. I take this over to the other side, and I get the integral of sine x e to the 2x dx plus what? A quarter sine x e to the 2x. Do you see I can combine those two? And what I have on this side is whatever is left. This. And since I no longer have an indefinite integral on this side, I'm going to have to put a constant. Or I should put a constant. But it's not going to be the constant I end up with, so I'm going to call it c hat. Now what happens is I combine these integrals. I got one integral, add a quarter of the same integral. That gives me 5 quarters of that integral, because 1 plus a quarter is 5 quarters. And then what's left is this plus c hat. Do you see now that I can solve for my original problem? I just have to divide everything by 5 quarters. And when I do that, I get the integral of sine x e to the 2x dx is, this is just dividing everything by 5 quarters, which is the same as multiplying by 4/5. What I'm going to get is 2/5 sine x e to the 2x minus 1/5 cosine x e to the 2x. And then I'm going to have 4/5 times this c hat, this constant. I'm almost there. 4/5 of an arbitrary constant is just an arbitrary constant, and so I'm going to call it c. Get it? And there I've done it. This integral is simply that. I say simply, do you notice it took us quite a while to get there? Okay, what is this technique called where eventually I get back to where I started and I pull it over to the other side? We call that back solving, and it happens often. Now I think I'll stop.